How do you analyze a dataset consisting of multiple measurements of the same group, as well as measurements from multiple different groups? Today, we're going to go over the Mixed Measures Two Way ANOVA. Hello, my name is Jacob from Intrepid Protoworks. Today, we're going to go over the code from start to finish on how to do a Mixed Measures Two Way ANOVA. We will also be doing an example on how to organize your data to work with this code. So we're starting off with our standard set of imports. We're importing math, scipy.integrate, decimal, and we're importing everything from it, CSV, so we can get our data file, random, and then from collections, we're getting ordered dict. And then we're going to set the precision of our decimal to 100. So I'll have 100 significant figures. We're going to do a simplified mean function. So we'll do def get mean, have it take a sample, and then I'll return the sum of the sample divided by the length of the sample. The next function we need to define will be a gamma function. We'll need to make our own for if we have large data sets with large degrees of freedom. Otherwise, the normal math.gamma will not work for us. We've been using this gamma function for several videos now, so we're going to go ahead and just speed through it. With the gamma function in place, we can do the f probability distribution function. This is going to be mostly the same as in previous videos, so we'll speed through up until we do the different part. The change we're making is pretty minor. We're just going to add a try except, where we will accept an overflow error. An overflow error occurs when our degrees of freedom value is too large for the regular math.gamma, and if that occurs, we'll use the gamma function that we wrote above. And while our gamma function may be horrendously slow, it still will work with a much larger value than the normal math.gamma function. Next, we'll go ahead and say if our f ratio is equal to 0, we'll just reset it to be very, very close to 0. That way we do not accidentally make our denominator 0 and end up with a division by 0 error. Our denominator is then just our f times our beta, and then that will give our PDF, which is the numerator divided by the denominator. We're going to go ahead and set those to float so we're not returning a decimal value. Then we just return the PDF value. The last function we need to write will just be a function to get our p-value from our f value and our degrees of freedom. And this is the same as what we covered in our f distribution video, so you can go ahead and reference that if you want to see that covered in more depth. And now with all that in place, we can go ahead and define our function for our mixed measures two-way ANOVA. It will take our data, it will take an alpha, and then it will also take a bool that will tell us whether or not we want to calculate the p-values. So we're going to go ahead and in some comments define some of our abbreviations. We'll say DOF is degrees of freedom, IF is independent factor, and DF is dependent factor. I'm going to add some comments in here because I've noticed a lot of English as a second language listeners or watchers to these videos. So you'll see a little bit more comments. So we're going to define degrees of freedom of the independent factor as the length of the data minus 1. Now to get at the other degrees of freedom, we need to look at the nested values, length of nested values, and the length of each dependent variable level. So we'll say that the IF key and the IF nested values is equal to next iter data.items. We'll then say the number of subjects per cell is equal to the length of next iter IF nested values dot values. With that information in place, we can now calculate the error of the degrees of freedom of the independent factor, which is the number of levels of the IF times the cell size minus 1. We also now have all the information to do the degrees of freedom for the dependent factor, and that's just going to be the length of the IF nested values minus 1. With that information now, we can go ahead and do the degrees of freedom for our interaction, and that's simply going to be the degrees of freedom for our independent factor times the degrees of freedom for our dependent factor. Now the last is the degrees of freedom for the error term of both the dependent factor and the interaction. To get this, we need to take the number of independent factors, multiply it by the number of dependent factors minus 1, and multiply that by the number of subjects per cell minus 1. Now we need to get the total number of measurements. So this is going to be the number of independent factors times the number of dependent factors times the number of subjects per cell. Lastly, we just need to get the degrees of freedom total, which will be the number of measurements minus 1. Now that we have all the different degrees of freedom we need, we can go ahead and make ourselves a little bit more space and start in on the different sums of squares. Go ahead and start on the sum of squares for the independent factor. The sum of squares for the independent factor is the sum of each of the independent levels of the independent factor squared divided by the number of levels of the dependent factor times the size of each cell minus the sum of all measurements squared divided by the total number of measurements. To get this into Python code form, we'll start by defining in an empty list. We'll call it each if level summed squared, and then we'll go ahead and make a set of loops that will go through our data. So we'll say for level values in data.items, our independent factor squared is equal to 0, so that will be set to 0 each independent level factor. We'll say for levels dependent values in level values.items. Then we'll make one more nested loop, which will go for row independent values. Finally, we can go ahead and add each row to the if squared, and then we can say the sum of each measurement is just plus equals row. We can then say the sum of each measurement squared is equal to the sum of each measurement squared. And we do the same thing for the sum of each if level summed squared. Now with that information in place, we can go ahead and calculate the sum of squares for the independent factor. And as described above, the sum of squares for the independent factor is the sum of each level of the independent factor squared divided by the number of dependent factor levels times the number of subjects. We then subtract the sum of all the measurements squared divided by the number of measurements. And now with that in place, we can go ahead and calculate the mean square. We'll go ahead and say ms is the mean square. And the mean square is the sum of squares divided by the degrees of freedom. So it will be the mean square of the independent factor will equal the sum of squares of the independent factor divided by the degrees of freedom of the independent factor. Now with that in place, we can go ahead and make ourselves some more space and then start in on the error term for our independent factor. To start out with this, we will go ahead and define a couple empty variables. We'll define current if as equal to 0, and then we'll define an empty list, each participant summed. We'll then do a for loop that is the length of the number of levels of our independent data times the number of subjects per cell. That'll give us the number of participants, and then for each of those, we'll just append a 0, which will give us a list full of zeros. That's the length of the number of participants we have. We can now go ahead and start our for loop, which will be for level values in data.items like we've done before. We'll then go ahead and do a nested for loop for level values, dependent values in level values.items. Now we need to go ahead and come up with our index for where we are at inside of our participant list. To do that, we'll go ahead and define a variable and call it participant in df, and we'll say it is equal to the number of subjects per cell times our current if. So for the first level of the if we go through, that'll end up counting 0, 1, and so on. For the next one, it will be 1 times the number of participants, so 5, 6, and so on. With that in place, we can now go ahead and do for row independent values, each participant summed, participant in df, so we're going through our index that we just came up for our participants, plus equals row. And then we iterate the participant in df, and we back out of that a couple levels and iterate our current if as plus equals 1. We can then go ahead and start with our calculations for our sum of squares. So we'll say each participant summed squared is equal to an empty list, and then we'll say for row and each participant summed squared dot append row squared. Go ahead and make ourselves a little bit more space real quick, and then we'll go ahead and define the sum of each participant summed squared as the sum of each participant summed squared. With all that in place, we can go ahead and calculate the sum of squares of the error for the independent factor. We'll call that the SSIF error, and that will be the sum of each participant summed squared divided by the number of dependent values minus the same factor as above, which we'll just go ahead and copy and paste that. We can then go ahead and make ourselves some more room and then go ahead and calculate the mean squares for the independent factor error. So MSIF error, and that'll be the same as before, the SSIF error divided by the degrees of freedom IF error. And now we have everything we need to calculate the F ratio, and that will be the mean squares, or the MSIF divided by the MSIF error. With everything with the independent factor done, we can start on the dependent factor. So we'll go ahead and start in on the sum of squares for the dependent factor. Start it off by defining an empty list called each df level summed. We'll then go ahead and do the same loop that we've been using. So for level values, and data.items. And we'll say current df level equals 0. And then we'll say for levels, dependent values in level values.items. Next we do something like before. We'll say if the length of each df level summed is less than 1. In other words, if we haven't filled it up yet, we'll say for I in range, the length of if nested values, each df level summed dot append 0. Our last nested loop will be for row independent values, and in it we'll say each df level summed, and then our current df level plus equals row, and then we'll back out of that loop, and then we'll increment our current df level plus equals 1. We will then back out, grab our list that we've just built, and then copy and paste it down below. We'll go ahead and add squared. We'll set that equal to an empty list, and we'll do a loop where we square each value within our each df level summed. And like before, we'll go ahead and make some space and then do a sum of each df level summed squared by using the sum function. We now have all the information in place to be able to calculate the sum of squares for a dependent factor. So we'll define that as SSDF, and we will go ahead and paste in our sum of each dependent factor level summed squared, and we'll divide that by the number of levels of our independent factor times the number of participants per cell, and we'll divide that by the term that we used earlier, which is the sum of each measurement squared divided by the total number of measurements. And again, we'll go ahead and calculate the mean square of the dependent factor. This time it'll be the sum of squares of the dependent factor divided by the degrees of freedom of the dependent factor. Now we will go ahead and skip the sum of squares for the error term of the dependent factor and go ahead and do the sum of squares for the interaction. And to start ourselves off, we'll go ahead and define an empty list called each cell summed squared, and then make ourselves some more space. In that space, we'll go ahead and start our set of for loops. We'll say for level values in data.items, and then immediately for levels, dependent values in level values.items, and then we'll go ahead and have our cell total equals 0. That way, each time we go through a level of the dependent factor, we will reset to our cell total. And we'll say for row independent values, cell total plus equals row. We'll back out of that loop and we'll say each cell summed squared dot append, and then our cell total squared. We can then back out of our set of nested for loops and then define the sum of each cell summed squared as the sum of each cell summed squared. With that in place, we can now calculate our sum of squares interaction, defining it as SS underscore interaction. Our first term in the sum of squares for the interaction is the sum of each cell summed squared divided by the number of subjects per cell. For the next term, we can go ahead and go up to our sum of squares for our independent factor and then grab the sum of each IF level summed squared divided by our number of independent factor levels times our number of subjects per cell. And then we can go ahead and grab from our sum of squares df, the sum of each df level summed squared divided by the number of independent factors times number of subjects per cell, and then adding our sum of each measurement squared divided by our number of measurements. With this in place, we can do our mean square interaction, which is equal to our sum of squares interaction divided by our degrees of freedom interaction. The next sum of squares we'll go ahead and calculate is the sum of squares total. After making some space, we will go ahead and define each measurement squared as equal to 0. And we'll make our same set of loops that we've been using. So for level values in data.items, for levels, dependent values in level values.items, and then for row independent values, we'll do each measurement squared plus equals row squared. then our sum of squares total will be each measurement squared minus the sum of each measurement squared divided by the number of measurements. To get this, we'll just subtract all the other sum of squares that we've calculated from the sum of squares total. Our sum of squares for the dependent factor and interaction error is the sum of squares total minus the sum of squares interaction minus the sum of squares of the dependent factor minus the sum of squares of the independent factor error and the sum of squares of the independent factor. Now, as a quick catch, we'll go ahead and add in an if statement, and if our sum of squares for the dependent factor interaction error is equal to 0 exactly, or whatever quirk of the data set that might be, we'll change it to be just really close to 0. What this does is prevent a dividing by 0 error down the line. And with that, we can go ahead and calculate the mean squares for the dependent factor and the interaction error as equal to the sum of squares of the DF interaction error divided by the degrees of freedom of the DF interaction error, which now means we can calculate the F ratios for both the dependent factor and the interaction, with the FDF equaling the mean squares of the DF divided by the mean squares of the DF interaction error, and the F interaction equaling the mean squares of the interaction divided by the mean squared dependent factor interaction error. And now we'll go ahead and proceed to evaluate whether or not each of these are significant. This is the same as what we've done in our two-way ANOVA and our other ANOVA videos, except we're doing it for an independent factor, a dependent factor, and an interaction. For a more detailed explanation of this part of the process, go ahead and reference some of our earlier videos. So we're going to go ahead and just speed through the rest of this up until our model table. Our model table is also very similar to what we've done in previous videos. If you also want to just reference the code, this will be up on our GitHub as well. So we're going to go ahead and just speed through making our model table. If you want to see a more detailed breakdown on how this model table is constructed or why it's constructed the way it is, you can go ahead and hit up our previous ANOVA videos. And to wrap up our function for our mixed measures two-way ANOVA, we need to go ahead and return our model table, degrees of freedom for independent factor error, and the degrees of freedom of the dependent factor and the interaction error. After fixing a quick typo, we are ready to move on to our example. For our example, we'll go ahead and start with our real data set from the American Community Survey. We'll define an ordered dict called data set, and then in that ordered dict define two empty lists, one with a key male and one with a key female. We'll then go through and open up our data like we've done in almost every video with the with open our file as new file data equals cpu.reader for row and data. We'll filter out the header. We'll filter out the non-applicable replies that are the 999. We will filter out anybody that made less than 5,000 or more than 200,000 because we kind of want to look at normal people. And then we will we'll filter by gender, sorting the people into either the male keyed list or the female keyed list. Because the data set that we just loaded into a couple of lists in our ordered dictionary is something about 3 million data points, go ahead and actually, for our example, just build a sample data set. And in our sample data set, we're going to go ahead and build a repeated measures factor. So we'll start off by defining the number of subjects. This will be convenient so we can play around with the number of subjects if we want to. And then we'll define the amount of gain for each level of our dependent factor. So min bonus, max bonus, and then we'll define our data sample as equaling an ordered dict. So then we'll define our data sample male before as equal to random.sample, and in that we will take from our data set male, and then for the number of lines of data, we will take the number of subjects. We can then go ahead and define our data sample male one class as equal to an empty list, and then we'll loop through our male before, and we'll define one class as equaling the income plus the somewhere between the range of our min bonus to our max bonus. We can then duplicate this process for 2 classes and 3 classes, and then we duplicate this whole process again for our female sample. With this done, we've simulated a repeated measures variable that we can then use for this example. If you are using a data set that you're bringing to this and you're trying to apply it to this data set, you can go ahead and use your own data set. You just need to make sure that you have the buckets, quote unquote, for each level of your dependent variable nested inside of each level of your independent variable. So similarly to what we've done in previous videos, we're going to define alpha is equal 0.05. We'll go ahead and say get p is equal to true for now. Then we'll say our results and our two error degrees of freedom are equal to the mixed measures two-way ANOVA. It'll take our data sample, our alpha, and get p. So we will go ahead and make ourselves some more space and then start in on outputting our results. This is similar to how we have done it in previous videos where we've output an ANOVA table with a couple of minor differences. So you can pause the video and take a look at what those differences are. If you want a more detailed breakdown about how this code works, you can go ahead and reference one of our previous ANOVA videos. The last step before we start testing our code is to go ahead and make a graph of our results. We've done this before. We'll use matplotlib.pyplot, and then we'll go ahead and use our style. We've explained all this in previous videos. We will go ahead and do a short loop that will give ourselves a list of means for each cell that we can look at. You can format this graph any number of ways. I would encourage you to play around it as your needs dictate. Now we just have to go through and troubleshoot some parts of our code. We need to do items instead of items. We will then go ahead and run our code again. So we have a local variable sum of each measurement reference before assignment. So we need to just go ahead and pop in an empty version of that up top, set it equal to 0. We then save and run again so it can try to find our next error. All right, so we have an invalid operation in our decimal class. So let's try to trace this back through. We don't need to look at modules from other code bases. We can be reasonably sure that that's not where the problem is. Let's see, so we'll get p from f, trace that back up further. We can see that there's an issue in our f probability distribution function. Let's go ahead and look through the information that goes into that. So we'll go ahead and print out our f, our degrees of freedom for our if, and our degrees of freedom for if error. Run our code again and see what prints out. All right, so we have our negative f ratio. That keys us in. So something is going wrong with calculating the f ratio for our independent factor. So we'll go ahead and print out the mean squares for independent factor and mean squares error for independent factor. And see that the mean squares for independent factor is negative. So let's go ahead and print the sum of squares of the if, and we can see that we need to change that to the degrees of freedom if. That's one error. Let's see what that changes. That does not fix the error. So let's look through our code and see what we can find for an issue. And we can see that we did not append our if squared to our each if level summed squared. So let's go ahead and do if squared and square that so the actual squared value is going into it, and see if that fixes the problem. So we've ran our code again and we have a typo though. So decimal, spell that correctly, and then run our code again. E is not defined. That's just a little oversight there. So E equals math.e. Run the code again. And we have output. We are now calculating our p values. That's taking too long, so let's figure out why that is. Change down the number of subjects. This is still taking too long. So let's go back and look at the main perpetrator for making this take a long time, which is our gamma function. And we can see that rather than dividing by math.gamma of a plus b, we're just doing gamma, which is our slower version of the gamma function. The math function's a lot faster. So we'll go ahead and fix that real quick and run the code again. So we have an error for our graph, and we also have our text not formatting correctly. So it's printing out the results being significant even if they are not. So let's go down to the bottom and take a look at what's going on. So we needed to change position to positions, and we need to go ahead and add the properly nested if statements. So we will go ahead and save and run our code, change get p to false real quick, and we have an indentation error. So we gotta go back and fix a little bit more, save and run again. And look at that, we have a properly formatted table. We have a couple print statements we need to get rid of. We have our graph. Let's go ahead and slide up the bottom a little bit so we can see sample incomes. And yeah, looks like everything's looking good. Go back, remove some of the print statements as we see them. change get p back to true, and run this again. See what we get. Let's go ahead and change the number of subjects. We'll go ahead and try 100 and save and run. Just looking through for my errant print statements real quick. Let's go ahead and expand this out, take a look. And yeah, it looks good. We can see our p values. You can see our f ratios. You can really see here how big the f value for a dependent factor can be and how sensitive a repeated measures factor can be. Now, let's go ahead and play around with some of these a little bit. We've played around with the number of subjects. Let's go ahead and play around with the amount of bonus. We'll set to 0 and see what happens. Our dependent or the significance should go away. Yep, we see that it went away completely. Now let's go ahead and change, just say that for whatever reason, there's awesome advice for females in the 3rd class. We should see a significant interaction. Yep, and the dependent factor is not significant as well. That's one thing to note. You always want to take a look at your data. Maybe it'll just be one factor creating an interaction that's carrying your dependent factor or something like that. So let's make the bonus bigger. We should see our dependent factor get huge now. Yep. You can see I got much bigger in magnitude. We also end up pulling from the independent factor is actually a legitimate factor showing statistical significance for the difference in income between men and women. So this time it wasn't significant. But then again, we're only pulling from, what was it, 50 people or something. If you have any problems with any of the code, be sure to take a look at the GitHub link. It'll be linked down below. And if you have any questions or comments, or you see an error that I did not see, please make a comment below and let me know what you think. We will be doing one more video in this main series for statistics. So next week we'll be doing a quick video on OLS regression. So again, if you have any questions, we've gone through a lot of topics. This is 3 hours of coding condensed into about 27 minutes. So please say something down below and don't forget to like and subscribe. Until next time, I'm Jacob from Intrepid Protoworks.